Okay. In later class, you guys will guided how you prepare the term project report. And the basic line is you have to write a professional looking report. It should include your layout analysis, such as list of departments, their requirement spaces, and their interrelationship and the flow between those departments. Once everything is done, you're supposed to draw relationship diagram, and the relationship diagram is also a design. There is no single correct answer. You have to find out the optimal relationship diagram, and based on that you are supposed to draw space relationship diagram, and then you're supposed to make the real layout. Well, you are highly encouraged to make some kind of growing algorithm or any other type of algorithm in developing this kind of layout. You know, the number of departments is around 20, so I think it's really hard to do it manually. Okay, so I strongly encourage you to utilize some computer software, your computer coding with MATLAB or Microsoft Excel or and the like. Okay, I will guide you how to do that in later classes. And bottom line is, after that, you are supposed to validate it. So I strongly recommend you to learn the Delmia Quest and run the simulation, because the load will be relatively heavy. So I've decided not to give homework number 4 originally. You know, on the course syllabus, you guys are supposed to have 4 different homeworks, but you only have the 3. One is remaining, but let's cancel it. Okay. Due date is the final exam date. So, and this is a team project. So you guys are one team, and the grade will be assigned to each of you. Team grade plus peer evaluation grade. So according to the final report, everybody will get the same grade. If the final report is really good, everybody will get A+ on the team project. However, there will be peer evaluation. You guys are supposed to evaluate other except yourself, and your team project grade will be the summation of the team grade plus peer evaluation grades. Question? Okay. Okay. On next Monday, TA will teach you about how to use the Delmia Quest for the very basics of this manufacturing system. And let's reiterate it. In previous class, we talked about the system, the real one, and the model, the abstracted one, and system state. And we also talked about everything depends on the level of detail you want to model the real system. If you want to model a system in a very detailed way, then it's up to you. However, the level of detail is relative term. However, it's all about system state. What kind of system state do you want to keep? That's the question which determines the level of details of your model. Okay. The reason the system state came first is really, really important. You know, sometimes, let's assume our university is a system and we want to model it, abstract it with some kind of model. Model has a purpose. If you want to visualize or simulate some academic interaction or maybe some epidemic disease epidemic behavior or something like that, well, we may have to model every single individual as a one entity. But if we are only interested in some kind of organization interaction thing, we don't have to model each individual as a one entity. Actually, that is kind of waste of time and energy, right? If you want to see the organization and their interaction, then why do we have to model each one of the students as an entity inside of the model? Okay, so each student is not affecting the system state as long as if we are only interested in the organization of the university, right? So if you are interested in the organization, then that's the system. And what would be the system state? Organization's state, department's state, their relationship, that's all. Because each individual has nothing to do with those kind of system state, we don't have to model each individual as an entity inside of your model. But think of it. This is a KAIST university, and we are interested in how the influenza spreads. You know, most of the time, some influenza will break out around maybe restaurant area, and it will spread, and eventually, it will reach the plateau area in terms of number of affected people. Then, number of people affected, number of healthy people, and each people's location and their user path will be very, very important system state in that case. Then we got to model each individual as an entity because they are required, because they affect system state. So logically, level of detail of your model, level of abstraction are heavily dependent on what kind of problem you are dealing with. Okay? And what kind of problem will automatically determine what kind of system state you have to deal with to model that, or to model those behavior of that system, right? And what kind of system state automatically determines what kind of entity do we have to have in the model. Okay, question? Okay. Attributes are the property of each entity, and it's also related to the system state. Entity only have meaning because it affects system states. And in that sense, we got to keep some kind of information about each entity, which we call attributes. List is just what we usually call, I think, it's a list. Okay, nothing nothing special there. And there is an event. When, discrete event simulation, as the title or name means, we consider events are discrete. Do you know what's the opposite meaning of the discrete? Continuous, right? We are not looking into the system in continuous way. Everything is discrete. Okay? And discrete event simulation, which means events are discrete. Okay? Events are not continuous. Events happens once, instantaneously. That's it. It happens instantaneously, and then it disappears. And it changes the system state. By the way, events are defined by those changing of system state. Okay? If something happens, but it doesn't affect any of the system states, then it's not an event. Okay? Cost organization interaction. If that's our problem, well, each of the organization and their information flow and the like will be the entity, and each of the entity will have relevant information as an attribute, such as level of hierarchy in organization chart or number of members inside of that organization and the like. But, opening the door cannot be an event in that kind of simulation because it does not affect any of those organization and things like that. However, if you're interested in the influenza epidemic, then moving of individual may change the system state, which means it could be an event in that case. Okay, event does not happen without any notice. This is computer software simulation. Even though this is an event, we have to know what kind of event will happen and when. And by doing it in computer, we are mimicking the system's behavior. Okay? So event notice is a record of an event occur at current or some future time. Okay? Event list is the list of the event. It's a future event list of the future event notice. That's what we call event list. And this FEL, future event list, plays a key role in this discrete event simulation system. Activity is defined as a duration of time. So it's basically time between events. But it's not always true, but basically the meaning is that. For example, when a part enters to a machine, do we know how long does it really take? Yeah. If a part comes in a machine, after one cycle time, the process will be done. So after one cycle of time, I don't know, but it may be 1 hour, 1 week, or it will come out of that machine, and a new part waiting for processing will enter the machine, right? So the duration of time, in this case, activity, the cycle time will be the activity of that dynamics. Okay? Delay means duration of time of unspecified indefinite length which is not known until it ends. Sometimes there are a variation, so those variations interact with each other. For example, for a part, it requires some time of processing, but it cannot be, it sometimes requires more time to finish those required processing because some parts are already occupying the machine, or machine could be break down or something like that. So it could be delayed. That's the delay, definition of the delay. And the clock. Everybody know what the clock is. And in this discrete event simulation world, the clock is different from our world clock. The real world's clock, what we call world clock, like this, but in simulation world, clock is different, and we call that clock as a clock. Simulating a month of manufacturing. If simulating a month of manufacturing requires a month, then what's the good of this simulation? Right? So in computer simulation mode, we can fast forward the time flows by manipulating the simulation clock, which is different from, or could be same as, the world clock. Okay? Questions so far? Okay. Okay, let's explain this one in more detailed manner. Here is one example. A single channel queue. Consider a small grocery store with one checkout counter. Customers arrive at this checkout counter randomly, but we know the range of this randomness and the service time, calculating their groceries. Service time is also a random thing, but we know the ranges. Okay, that's the usual situation we can think of. Okay, queue means some buffer. It's a first in, usually first in, first out, or first in, first served buffer. So what you call, there is a usually server, and we draw buffer like this. Thing is usually like this. Queue is same thing like waiting line. Okay? And population is group of the customer. Okay? So customer arrives into the waiting line. If nobody's in the waiting line, then go directly to the server and being served. And once service is done, it go back to the original population. That's how it works. Okay? When the customer arrives, this is random thing. Sometimes it could arrive in multiple customers at the same time. Sometimes one customer after a very long time, when the other customer come to this system. Okay, so when customer arrives to the queue, but some customers are waiting in the queue, it has to wait until the all waiting customer in front of him are being served. Okay, it's a very straightforward. It's a waiting line. That's the single channel queue. Sometimes this is possible. You know, even though there is a one waiting line, there could be multiple parallel server, right? And as you can easily see, they are usually the capacity of the queue, waiting line. The length of the waiting line means the capacity of the waiting line, how many customers it can hold in that waiting line. In real world, the capacity is limited, but in virtual world or in our classroom case, we usually take this waiting line queue as has infinite capacity because it's more easier to analyze. Okay, but anyway, queue could have the capacity, and server has usually the service time. Okay, and usually population could be limited, but the most simple one is unlimited size of the population. For example, the things like this single channel queue are one. Let's assume home plus, and let's assume there is only one checkout lane. This is the system. Okay? But by changing this queue, size of the queue or size of the population, we can model the relevant real system. Let me think of some example. You are the distributor of the Burger King patty, working for Burger King company. I don't know they are working like this or not, but your coverage area is Daejeon area. Okay? Other than that, that's not your job. Your job is to provide enough patty for Burger King store inside of the Daejeon. And let's assume inside of the Daejeon there are 10 different Burger King stores. So your customer, so your job is whenever they call, we need more patty, please deliver 100 patties to our store. If you get the call, you have to deliver it. Okay? Can understand your situation? Then who is the customer and who is the server in the case? Who provides the service? Me. You are the only server. Who are the customers? Burger King store. Their number? 10. It's not unlimited. In that case, you got to set your population is size of 10. Which means, if you're waiting, by some chance, 10 customers could wait inside of your queue, right? Then you know that there is no left in the population. By manipulating the number of population and by manipulating number of queues and by manipulating number of servers and number of parallel servers, you can solve variety of the problem. Or this one could also happen. Queue, server, queue server. Sometimes queue multiple server, multiple parallel server, queue multiple parallel server, queue multiple parallel server. Basically, if you model like this, you can model the manufacturing plant. Okay? Okay. Let's think of this example. Unlimited population, and customer arrives to the queue from 1 to 8 minutes apart, and we call this is inter-arrival time. Okay, and service time varies from 1 to 6 minutes. Okay, and we can observe the real world like a Burger King checkout line or Home Plus checkout lane, and we can measure their service time one by one and get the stat data and calculate the statistics, and we can say, well, it depends, but the mean service time is this much, and the distributed like that, and standard deviation is like that, and it's a probability thing. We can gather those kind of data, right? Inter-arrival of the customer, we can do the same thing, right? And if we build this kind of system and data acquired from the real world, we can also model as an unlimited queue or limited queue, but we know how the system is look like, and then once this is set, we can solve those kind of problems, such as what would be the mean average waiting time for customer to check out. Okay, for example, Burger King company, they want to reduce the customer's waiting time less than 1 minute, right? Based on that case study. In this system, can you do that? Or what would be the average length in the waiting line? If this is 10, or it's a 20, it's a 5. Based on that observation, we can design the optimal length of the waiting line. Okay, if such kind of question are very, very essential in designing a manufacturing system, or in turn, layout can be solved by this kind of simulation. Okay, well, this system is really, really easy because the system is so simple, so it is possible to analytically solve it with your knowledge. We know, EOQ model, QR model, or news vendor model, and the like. We have those kind of things. If you do the calculation, then you can easily derive. You can easily answer the question I just asked. But the goodness of this discrete event simulation comes here. For the simplest possible, this one, we can do it. But, well, if this one is interconnected each other and becomes a very complex and long one, server, queue, multiple server, and split queue, multiple server. And usually the many kind of manufacturing system will look like this, and there is no way to analytically solve it. But discrete event simulation system, we can simulate it. Okay? Okay, this is calculated like this. we said inter-arrival time is randomly distributed and their range is 1 to 8 minutes, right? So time between arrival, which means inter-arrival time, is 1 to 8. All things listed. And we just assume that the probability, it's a uniformly distributed random thing. So probability for each of the case is 1 over 8, 0.125. So evenly distributed. And based on this probability, we can calculate the cumulative probability function by summing up from, you know what this column means, right? This one just same as this, and this plus this is this, this plus this is this, this plus this is this. And eventually this cumulative probability should be 1 at the end, right? It's a probability and it's accumulation of that probability. And this is a random digit assignment thing. You don't have to do this kind of step, but it just explains how we can generate this inter-arrival time randomly. In this case, we assume that we have random number generator. If we click the button, it automatically generates random number from 001 to 000, from 1 to 1000. And this random number generator inside of your calculator or computer are usually good at generating this. From 0 and 1 and uniform probability, right? Okay, we assume that this inter-arrival time is uniform. So we don't have to do this kind of step. The reason why we build this kind of table is using this uniform random number generator, we can create almost any form of random distribution. What if this inter-arrival time distribution of a customer is normally distributed? Then what we change this probability thing here, okay? 4 and 5 has the highest possibility and 1 and 8 will be tailed down like this. And okay. If it's distributed like this, the next step is make this cumulative distribution function, and it also ends like this. And random digit assignment means from here this is 1 to 8 minutes, right? Random number assignment means dealing with this from 001 to 1000, and based on some random number generation, what we'd like to do is this, right? If this is a uniformly distributed function, then it's going to be this. Same thing. The shape doesn't matter if we follow this step. It could be log shape, exponent shape, or whatever shape it is, we can transform that into the cumulative probability function, which is always monotonously increasing function. So we can do this. You know the meaning of this table? It explains how we can utilize random computers random number generator into some distribution following random number. Okay. By doing this, we can easily utilize our computer to make randomly generate inter-arrival time. We can do it for the discrete number from 1, 2, 3, 4, 5, 6, 8. We can do it for the continuous number as well, right? Okay. Let's assume that we successfully generate this inter-arrival time. No problem until now, right? Really? Okay. We can do the exactly same thing for the service distribution. As I said, service time required is also randomly distributed from 1 to 6. So, service time. But now, I assume that it is not uniformly distributed. It has some kind of shape inside of that probability, which means service time of 1 minute will happen the probability of 10%. The service time of 3 minutes will happen with probability of 30%. So, looking at this probability, we can guess that the customer usually requires 3 or 4 minutes of service time, right? And also we can easily transform into the cumulative probability function, and then we can assign random number digit, and we can easily generate randomly the service time. Any question so far? I'm talking about how we can simulate it in computer. And even though we have the statistics, because everything is random, we got to have some kind of tool to transform these statistics back to the random numbers, right? Because computer does not directly calculate the statistics. It runs the random number generator, and based on this thing, it generates the random service time, inter-arrival time, and then it do the simulation. Any questions so far? Okay. Numbers. Okay. Let's take a 10-minute break at this point, because numbers is the Macintosh software which cannot run here. I need to bring my Mac or have to transform it into the Microsoft Excel, but I will show you when we resume in the class. Okay. Okay. In this system, we can do the simulation like this. First one is the customer. Simulation starts when the customer starts to move in our system. The first one will arrive, and then second, third, and the like. So the first column is assigned to the customer number, and I just do the manual simulation until I have the 20 customers. Okay. It can be specified, but however, I assume that at the beginning of the simulation, the first customer just arrived. It's my assumption, but you don't have to follow that assumption. So if you assume that first customer arrives when the simulation begins, well, we don't have to have random digit for that, because we don't need any random number generation. So clock time of the arrival of the first customer is 0 at the beginning. Okay. Here, done. Okay. And we keep run running the random number generation, and by by some chance the second random number generated was 913, and the third was 727, and the like. So this one are the random number generated. It could be randomly changes, but anyway, if it is 913, then based on this 913 falls into this one, so inter-arrival time will be 8, right? So time between arrival is 8. You know, inter-arrival time is not the clock. It's a time after the previous customer arrives. So the clock of the previous customer arrives at time of 0. So 0 plus 8 is 8. Okay? Third customer, by some chance, the inter-arrival time randomly generated is 6. So the actual arrival time of this third customer is 8 plus 6. So it's 14. Any question here? By repeating it, we can generate that this. First customer arrives to the system at the beginning. Second customer arrives at 8 minutes. Third, 14 minutes. Fourth, 15 minutes. Fifth customer, 23 minutes, and the like. Okay, so 20th customer arrives in the system at 82 minutes. Okay, any question in generating this arrival of customer to the system? Okay, you can ask the question to me, Sang-hwan. What was the question? Okay. For this, we run the random number generator. Okay, and based on that, we calculate the inter-arrival time, and based on that, we calculate the clock of arrival of the customer. Okay? This one is also random. So we run the random number generator once again. So randomly, it was 84. 84 falls into here, service time of 4. So service time is 4. Okay? And then 10, 1, 20. So based on this random number generation, we can easily determine the service time required. It's a randomly generated. However, this one means service time randomly distributed based on our observation, right? Any question until now? Okay. Important thing is here. Okay. In the beginning, the customer first arrives. So arrival of the customer and service begins instantly because there is nothing waiting in front of the first customer. Okay, so service time begins initially, and because of that, the first customer don't have to wait in the line, so it's just 0. And service time ends means at 4 because no wait, and service requires only 4 minutes, so service ends at 4. Okay, and customer only spends this 4 minutes because it's a service time plus waiting time. Waiting time is 0, service time is 4, it's a 4. Idle time of the server. So server was idle until for this customer number 1, no, it was busy. Okay? Straightforward, right? Okay. Service time begins. Can you see this thing? If I highlight this, It's a maximum of this and this. Okay? This means service ends time of the previous customer, and this one is the current customer's arrival time. So in this case, the second customer arrives after the first customer's service was done. Okay? So it starts 8, right? Any question here? And the service starts 8, right? But service ends at 4. So 8 minus 4. During 4 minutes, server was idle because it doesn't have any customers to serve. Okay? Okay? And the second customer requires only 1 minute of service time. Okay? And since there is no no customer waiting in front of him, it don't have to wait in the queue. So 0 time wait. And 8 plus 1 is 9, right? Service begin plus service time. So it ends in 9, time 9. And, you know, this one is waiting time plus service time. So this customer number 2 spends only 1 minute inside of this system, and it is explained before. Okay, question so far? And the next, the third customer, it arrives into the system at time 14. Okay, and this one is also the maximum of value of these two. So the previous customer's service was completed in time 9 and it arrives at 14. So 14 minus 9, 5 minutes of time, the server was idle and it arrives at 14 and it requires 4 minutes. So service time begins at 14 as long as it arrives and don't have to wait in the queue. And after 4 minutes, which is 14 plus 4, service ends at 18. Okay? And time customer spends in the, so 0 waiting time for 4 minutes of processing time is 4. Okay? Okay, here comes a little complex thing. Fourth customer arrives at time of 15. Okay? So service time is maximum of these two. When it arrived, but the service was not ended. Okay? It arrives at 15, but service time ends at 18, right? So service can only start at 18. Because of that, 18 minus 15, it has to wait 3 minutes. It's a delay, okay, by the way. It has to wait inside of this queue 3 minutes, and the service starts at 8, and 8 plus 3 required service time is 21. So the service ends in 21, and 6 means 3 minutes of waiting time and 3 minutes of service time. It's a 6. The idle time, there was 0 because customer was waiting for the server. And if you keep doing it, you can do until the last customer enters and leaves the system. Any question about this table? This is how this discrete event simulation is done. And important part is the statistics. Things like this. Service time. The summation of the service time is 6 to 8. Okay? And based on this number, I mean 68 divided by 20 customer, you can easily calculate the average service time. And time customer, if you calculate, summarize all this one and divide by 20, it's a average waiting time inside of this queue. Okay? Idle time. Well, you know what I mean. So, step by step, we do simulate like this and gathering each of the statistics of this simulation result, and we can answer those kind of questions utilizing the discrete event simulation. Important thing is like this. Those service time 4 minutes, 1 minute, 4 minutes, this is the time duration. It's a activity. It's being served. But think of this system. How do you represent the system's state? With what system variable you can fully explain the system? Well, system is there, model is there. There is a one queue, one server, unlimited length of the waiting line, unlimited number of population. Then it's a model. But you need to explain the current state. It's like a picture taking. Current state. How can you explain it? What's the minimum variable to explain this system's state? Well, since we assume this is unlimited number, important thing is how many customers inside of this queue, and it's being served. This server is busy or idle. If we have these two variables, I can explain 100% of this system state. Am I right? Are there any other system state do we need? Okay, that's the system state. Number of customers inside of this queue and server idle and busy. But however, there are dependencies. If there are customers are waiting, but the server is idle, it's not possible state, right? In this model. If customers is waiting, the server should be busy, right? Because based on our model. So there is some kind of relationship in this number of customer waiting in the queue and the server state idle and busy. So this kind of system can be expressed in various ways, but however, the number of the variable is only 2, right? Okay, that's the system variable, system state. What is changing? What kind of event can change the system's state then? What kind of occurrence changes the system's state? What increase or decrease the customer waiting for in the queue? Arrival of a new customer and processing is done. There's 2 events available. Events is the occurrence that affect, that changes system's state. Arrival and service done. 2 events. If we have this kind of 2 events, then we can modify the system's state, right? Plus, there is a common event such as simulation starts and simulation terminates. If we have these 4 events, then we can do the simulation of this simple system. So that's the 4 events. Okay? Question? Okay, if you look at this thing, customer number, we summarized everything by the customer's arrival and departure, right? This row, arrival and departure, is kind of mimicking discrete events. We are not talking about anything like what will happen at the time when the clock is equal to 10. There is no nothing. Because at time is 10, the system state does not change at all. Okay? When second customer arrives and second customer leaves and third customer arrives, third customer leaves, those arrival and leave of the system is the event. And between the event, system state does not change. Okay? And we proceed event to next event directly, because during this event, nothing is changes. So we don't have to look into this event. Okay? Question? Okay. This is system state of the system we are talked about. Number of customers in the waiting line and number of being served or not. If server is busy or not, 0 or 1. If we know these two, we can explicitly express our system. Yep. Your faces tells me that you guys are unhappy about it. You know, here is a cylinder, diameter and length. If you have these two variables, you can 100% explain the cylinder. Am I right? Am I right? What kind of other parameter do you need to express a cylinder? That's it. Well, diameter versus radius, well, you know, it's the same thing, right? Number of customer in the waiting line or idle or busy. It's a 2 parameter. Well, somebody can argue that diameter is double of the radius, so, or, you know, if you know the volume and the height of the cylinder, then it's also 2 parameter, and you can 100% express the cylinder. Am I right? Yeah, things like that. You only need these two. Can be expressed in other terminology, but you only need these two. Okay. Entities, you know, as I explained, level of detail here, level of abstraction, level of detail are about the system state. If you only want to, how many, you know, if your interest is how many, customers' usual waiting time and user server service time and the like, this model is just enough. Okay, if you need to answer more detailed questions, like A's, I don't know, but if that's the case, you need more detailed system state to actually can capture those detailed questions. But anyway, this is the just enough modeling, and system state is true, customer, ID or being, and entity are dependent on the system state. You know, number of customer is important. Which customer doesn't matter in this case. So we don't have to explicitly make customer entity here. Okay? In manufacturing system, if it is a one single very long line of queue and server, queue and server, queue and server, then we don't have to explicitly distinguish the part here and part there and part there. Everything is same. But if you're interested in different type of production part, such as described in this team project, they manufacture chair type A, chair type B, tables, desk chairs, and the like. Then you have to distinguish it, right? This is really important. How many chair A type is manufactured and or the usual waiting time for the type B chairs are important, so you have to distinguish it. So in that case, you have to have those kind of entity, right? Okay. Events. It's a thing, occurrence that changes the system variables, and as we discussed, arrival of the customer and departure of the customer is the event. You know, stopping event is important. When this one happens, simulation will stop. Without it, computer will continuously simulate it. So we need starting and ending events. Usually, they don't need starting events. Usually, when time is 0, it starts. And you know, stopping events can be such as at time 60, stop it, or when you have the 20 customer is processed, stop. Those kind of stopping condition is required. It's an event. It changes system variables other than stopping and starting events. Okay. Events notice is the events with time information in it. So arrival events happens at time t. Departure event happens at time t. Okay? Let's go back to our Excel here. Yep.
So in this system there are 2 events or 3 events?
2 events or 3 events?
In this system.
Basically 2, arrival and departure, and any kind of simulation requires basic 2, starting and ending events.
There on the slide
Except starting and ending, it has only 2, arrival and departure. What?
Sorry,
Except the basic simulation event, which is the starting and ending, arrival and departure, only 2. Look at that. Here, arrival 0 at time 0. It's a event notice. Arrival will happen at time 0. Arrival will happen at time 8. Arrival will happen at time 14. Arrival will happen at time 15. This is event notice. We previously know this arrival events, when these arrival events will happen based on this random number generation. right? Departure, let's go back. It is a little complex here, but departure is the ends of the service. When services ends, customer automatically depart. So at here, customer number 1 will depart at time 4. Customer will depart at time 9, 18, 21. This is departure event notice, right? At time 6, whenever time it is, it should end. That's the thing. Any question about this? Okay. Activities, I explained that it's a time duration. Okay, so such as inter-arrival time and service time. It's activity. Delay. Customer is waiting in the waiting line, then it's a delay. Okay. This shows some logics how these arrival events are executed in the system, but it's exactly same as I explained in this Excel sheet. Okay. Look at that. The arrival event occurs at some time is it's ls, I guess. LQLS. I think it's ls. At that time, it's ls is 1. ls is 1 means server is busy, right? If server is busy, yes, increase LQ by 1. If server is busy, it should be go here. If server is not busy, then let it change it to busy. LQ is changes. Both way, when arrival events happens, it changes LS or LQ or LS, either way, which is the system variable. So event changes system variables. And cannot see because it is a time advance function. Time advance, as I explained here, we know even though it starts at time 0, it requires 4 minutes of the service time, and we don't have to count the time between 0 and 4 minutes. We just can go to the time 4 directly because nothing is changing the system variable. Okay? Which is explained here, and if you keep doing this, you can run. Anyway, this flow chart is what I just explained with this Microsoft Excel sheet. So another thing, execution of departure event and overall structure of event scheduling are expressed here. Okay. Let's see this future event list. Then time is up. So I will resume it here. I will call it a day at this point, and let's resume on next Wednesday class. On next Monday, TA will introduce about how you can use Quest discrete event software. Okay, thank you.